Okay, so once again, good morning, everyone. So our topic for today is a computer systems overview, a continuation. So now, how about the memory hierarchy? No? The designs constraints a computer's memory can be summed up by three questions: how much, how fast, how expensive. The questions of how much is somewhat open-ended. If the capacity is there, applications will likely be developed to use it. The question of how fast is, in a sense, easier to answer. To achieve greatest performance, the memory must be able to keep up with the processor. So that is, as the processor is executing instruction, we would not want it to have to pause waiting for instruction or operands. The final questions must also be considered. For a practical system, the cost of memory must be reasonable in relationship to other components. As might be expected, there is a trade-off among the three key characteristics of memory, namely capacity, access time, and cost. A variety of technologies are used to implement memory systems, and across this spectrum of technologies, and the following relationship hold: faster access time, greater cost per bit; greater capacity, smaller per bit; and greater capacity is lower access speed. Now, okay, again, the dilemma facing the designer is clear. So the designer would like to use memory technologies that provide for larger capacity memory. So both because the capacity is needed and because the cost per bit is low. However, to meet performance requirements, the designer needs to use expensive, relatively lower capacity memories with fast access times. The way out of this dilemma is not rely on a single memory component or technology. Again, however, to meet a performance requirement, the designer needs to use expensive, relatively lower capacity memories with the fast access times. Also, the way of this dilemma is not really, or this is not rely on a single memory component or technology, as I mentioned, but to deploy a memory hierarchy. A typical hierarchy is, of course, one goes down the hierarchy and the following occur. No? Decreasing cost per bit, increasing capacity, increasing access time, and decreasing frequency access to the memory by the processor. So it means that smaller, more expensive, faster memories are supplemented by larger, cheaper, slower memories. The key to the success of these organizations is the decreasing frequency to access at lower levels. So, of course, we will examine this concept in greater detail in some other discussions. So, when we discuss the cache, or cache, and when we discuss virtual memory later, in our discussion in other chapter. Now, suppose that the processor have access to two levels of memory. So, level 1 contains, for example, 1,000 bytes and has an access time of 0.1, of course. Then level 2 contains 1,000 bytes, and has an access time of 1. So assume that if a byte to be accessed is in level 1, then the processor accesses it directly. So if it is in level 2, then the byte is first transferred to level 1 and then accessed by the processor. So for simplicity, Okay. For simplicity, sometimes we ignore the time required for the processor to determine whether the byte is in level 1 or in level 2. So, in this figure actually, no, figure 1.14, again, as what we have here, no, we have an offline storage, a magnetic tape, then outboard storage, and the magnetic disk, no, that which you are all familiar. The inboard memory, with the inboard memory, we have the main memory, cache, and the registers. In this figure, no, it shows that the general shape of the curve that models the situation. The figure shows the average access time to a two-level memory as a function of the bit ratio of H, where H is defined as the fraction of all memory accesses that are found in the faster memory. So T sub 1 is the access time to level 1 and T sub 2 is the access time to level 2. No? As can be seen, for the high percentage of the level 1 access, the average total access time is much closer to that of level 1 than that of level 2. No. So in our example, suppose 95% of the memory accesses are found in the cache, so H is equal to 0.95. Then the average time to access a byte can express as, of course, 0.95 multiplied by 0.1, no, plus 0.5 multiplied by 0.1 plus 1 is equal to 0.95 plus 0.0055 is equal to 0.15. So the result is close to the access time of the faster memory. So the strategy of using two memory level works in principle, but only if conditions, no, true in the preceding list apply. So by employing a variety of technologies, a spectrum of memory system exists that satisfies condition A through C. And fortunately, conditions D is also generally valid. So for the basis or the basis for the validity of condition D is a principle known as locality of reference. So during the execution of a program, memory referenced by the processor for both instructions and data tend to cluster. So programs typically contain a number of iterative loops and subroutines. So once a loop or subroutine is entered, there are repeated references to a small set of instructions. Similarly, operation on tables and arrays involve access to a cluster set of data bytes. Over a long period of time, the cluster in use change, but over a short period of time, the processor is primarily working with fixed clusters of memory references. Accordingly, it is possible to organize data across the hierarchy, such as the percentage of accesses to each successively lower level is substantially less than that the level above. No, considering the two-level example already presented, let level 2 memory contain all program instruction and data. Then the current clusters can be temporarily placed in level 1. So from time to time, one of the clusters is in level 1 will have to be swapped back to level 2 to make room for a new cluster coming into level 1. On average, however, most references will be 2 instructions and data contained in level 1. So again, the principle can be applied across more than 2 levels of memory. And the fastest, smallest, and most expensive type of memory consists of the registers internal to the processor. So typically, a processor will contain a few dozen such as registers, although some processors contain hundreds of registers. Skipping down 2 levels, main memory is the principal internal memory system for the computer. And each location in main memory has a unique address. And most machine instructions refer to one or more main memory addresses. Again, main memory is usually extended with a higher speed, smaller cache. So the cache is not usually visible to the programmer or indeed to the processor. It is a device for staging the movement of data between main memory and processor registers to improve performance. So, there are three forms of memory just described, no? Typically, volatile and employ semiconductor technology. The use of three levels exploit the fact that semiconductor memories comes in a variety of types, which differ in speed and cost. Data are stored more permanently on external mass storage devices, take note of it, of which the most common are hard disks and removable media, such as removable disk, tape, and optical storage. So external non-volatile memory is also referred to as a secondary memory or auxiliary memory. These are used to store program in data files and are usually visible to the programmer only in terms of files and records as opposed to individual bytes or words. So a hard disk is also used to provide an extension to main memory known as virtual memory. Additional levels can be effectively added to the hierarchy in software. So for example, a portion of main memory can be used as a buffer to temporarily hold data that are to be read out to disk, such as technique, sometimes referred to as a disk cache. It improves performance in two ways, like these writes are clustered instead of many small transfer of data. And we have a few large transfer of data. This improves disk performance and minimize processor involvement. Some data destined for write out may be referenced by a program before the next dump to disk. In that case, the data are retrieved rapidly from the software cache rather than slowly from the disk. Now, the cache memory. Although cache memory is invisible to the operating system, it interacts with other memory management hardware. So furthermore, many of the principles used in virtual memory schemes are also applied in the cache memory. So now, okay, a motivation. On all instruction cycles, the processor accesses memory at least once. So to fetch the instruction and open one or more additional times to fetch operands and or store results. So the rate at which the processor can execute instruction is clearly limited by the memory cycle time. No, the time it takes to read one word from or write one word to memory. And this limitation has been a significant problem because of the persistent mismatch between processor and main memory speeds. Over the years, processor speed has consistently increased more rapidly than memory access speed. So therefore, we are faced with the trade-off among speed, cost, and size. Ideally, main memory should be built with the same technology as that of the processor registers, giving memory cycle times comparable to processor cycle times. This has always been too expensive a strategy. So the solution is to exploit that principle of locality by providing small, fast memory between the processor and main memory, namely the cache. So how about the cache principles? So cache memory is intended to provide memory access time approaching that of the fastest memories available and at the same time support a large memory size that has the price of less expensive types of semiconductor memories. The concept is illustrated here in our figure. No, there is a relatively large and slow main memory together with a smaller, faster cache memory. So the cache contains a copy of a portion of main memory. So when the processor attempts to read a byte or word of memory, a check is made to determine if the byte or word is in the cache. If so, the byte or word is delivered to the processor. If not, a block or main memory block memory consisting of some fixed number of bytes is read into the cache and then the byte or word is delivered to the processor. Because of the phenomenon of locality of reference, when a block of data is fetched into the cache to satisfy a single memory reference, it is likely that many of the near future memory references will be to other bytes in the block. Okay, how about, this will be for the single cache. How about the 3-level cache memorization? So in this figure, it defects the use of multiple levels of cache. So the L1 cache is slower and typically larger than the L1 cache. And the L1 cache is slower, the L3 cache is slower and typically larger than the L2 cache. Now, in this figure, it defects the structure of a cache or main memory system. So main memory consists of the 2 raised to n addressable words, with each word having a unique n-bit address. So for mapping purposes, this memory is considered to consist of a number of fixed length blocks of k words each. That is, there are m is equal to 2 raised to n divide k blocks. So cache consists of c slots, also referred to as lines, of k words each, and the number of slot is considerably less than the memory of main memory blocks, or the c less than m. Then some subset of the blocks of main memory resides in the slot of the cache. So if a word in a block of memory that is not in the cache is read, that the block is transferred to one of the slot of the cache, because there are more blocks than slots. An individual slot cannot be uniquely and permanently dedicated to a particular block. So therefore, each slot includes a tag that identifies which particular block is currently being stored. The tag is usually some number of higher order bits of the address and refers to all the addresses that begin with that sequence of bits. Now, a detailed discussion of cache design is beyond the scope of our discussion actually. So the key elements are briefly summarized here. So we will see the similar design issues must be addressed in dealing with virtual memory in this cache design. So they fall into the following categories: the cache size, the block size, mapping, mapping functions, replacement algorithm, write policy, and number of cache levels. Now, we have already dealt with the issue of cache size. So it turns out that reasonably small caches can be a significant impact on performance. So another size issue is that of block size, the unit of data exchange between cache and main memory. So as the block size increases from very small to larger sizes, the hit ratio will at first increase because of the principle of locality. The high probability that data in the vicinity of a reference word are likely to be referenced in the near future. So as the block size increases, more useful data are brought into the cache. The hit ratio will begin to decrease. However, as the block becomes even bigger and the probability of using the newly fetched data becomes less than the probability of reusing the data that have to be moved out of the cache to make room for the new block. So when a new block of data is read into the cache, the mapping function determines which cache location the block will occur or occupy. So two constraints affect the design of the mapping functions. First, when one block is read in, another may have to be replaced. We would like to do this in such a way as to minimize the probability that we will replace a block that will be needed in the near future. So the more flexible the mapping functions, the more scope we have to design a replacement algorithm to maximize the hit ratio. Second, the more flexible the mapping functions, the more complex is the circuitry required to search the cache to determine if a given block is in that cache. The replacement algorithm chooses within the constraint of the mapping function. So which block to replace when a new block is to be loaded into the cache, and the cache already has all slots filled with other blocks. So we would like to replace the block that is least likely to be needed again in the near future. Although it is impossible to identify such a block, a reasonably effective strategy is to replace the block that has been in the cache longest with no reference to it. This policy is referred to the least recently used, or the LRU algorithm. So hardware mechanisms are needed to identify the least recently used block. If the contents of a block in the cache are altered, then it is necessary to write it back to the main memory before replacing it. The write policy, so the write policy dictates when the memory write operations takes place. So at one extreme, the writing can occur every time that the block is updated. At the other extreme, the writing occurs only when the block is replaced. So the latter policy minimizes memory write operations but leaves main memory in an obsolete state. And this can interfere with multiple processors operations and with direct memory access by input-output hardware modules. And finally, it is not commonplace to have multiple levels of cache. Level L1 or cache closest to the processors, L2 and many cases a third level L3. Also, discussions of the performance benefits of multiple cache levels is beyond our scope for a discussion. Okay, how about the direct memory access? Three techniques are possible for input-output operations. Number one, program I/O, interrupt-driven I/O, and direct memory access. Now, before discussing DMA, we briefly defined the two other techniques. So when the processor is executing a program and encounters an instruction relating to I/O, it executes that instruction by using a command to the appropriate I/O module. So in the case of program input-output, the I/O module performs the requested actions and then sets the appropriate bits in the I/O status registers but takes no further actions to alert the processor. In particular, it does not interrupt the processor. Thus, after the I/O instruction is invoked, the processor must take some active role in determining when the I/O instruction is completed. So for this purpose, the processor periodically checks the status at I/O module until it finds that the operation is complete. So with program I/O, the processor has to wait a long time for the I/O module of concern to be ready for either reception or transmission of more data. So the processor, while waiting, must repeatedly interrogate the status of the I/O module. As a result, the performance level of the entire system is severely degraded. An alternative known as interrupt-driven I/O is for the processor to issue an I/O command to a module and then go on to do some other useful work. The I/O module or input-output module will then interrupt the processor to request service when it is ready to exchange data with the processor, because the processor then execute the data transfer as before and then resume its former processing. The interrupt-driven input-output, though more efficient than simple program I/O, it still requires the active intervention of a processor to transfer data between memory and I/O module, and any data transfer must traverse a path through the processor. So thus both of these forms of the input-output suffer from two inherent drawbacks. Number one, the input-output transfer rate is limited by the speed with which the processor can test and service a device. Number two, the processor is tied up in managing an input-output transfer. A number of instructions must be executed for the input-output transfer. So when large volume of data are to be moved, a more efficient technique is required. So direct memory access. The DMA or direct memory access functions can be performed by a separate module on the system bus, or it can be incorporated into an input-output module. In either case, The technique works as follows. So when the processor wishes to read or write a block of data, it issues a command to the DMA module by sending to the DMA module the following information. Number one, whether a read or write is requested. Number two, the address of the I/O device involved. Number three, the starting location in memory to read data from or write data to. And number four, the number of words to be read by or written. The processor then continues with other work. So it has delegated this I/O operations to the DMA module, and that module will take care of it. So the DMA module transfer the entire block of data one word at a time. So directly to or from memory without going through the processor. So when the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and end of the transfer. So the DMA module needs to take control of the bus to transfer data to and from memory. So because of these competitions for bus usage, there may be times when the processor needs the bus and must wait for the DMA module. We need to take note that this is not the processor process for one bus cycle, because the time it takes to transfer one word across the bus. No, the overall effect is to cause the processor to execute more slowly during a DMA transfer when a processor access to the bus is required. Nevertheless, for a multiple word input-output transfer, DMA is far more efficient than interrupt-driven or program input-output, or the direct memory access is far more efficient than interrupt-driven or program input-output. Now, the multiprocessor and multi-core organizations. Traditionally, the computer has been viewed as a sequential machine. So most computer programming languages require the programmer to specify algorithms as sequences or of instruction. A processor executes programs by executing machine instruction in sequence and one at a time. So each instruction is executed in a sequence of operations. So again, the fetch instruction, fetch operands, perform operations, and store results. So this view of the computer has never been entirely true. So at the micro operations level, multiple control signals are generated at the same time. So instruction pipelining, at least to the extent of overlapping fetch and execute operation, has been around for a long time. So both of these are examples of performing functions in parallel. Now, as computer technology has evolved and as the cost of computer hardware has dropped, computer designers have sought more and more opportunities for parallelism, and usually to improve performance and in some cases, so to improve reliability. So actually in this subject, or in this course, we examine the three most popular approaches to providing parallelism by replicating processors, of course, symmetric multiprocessors, multi-core computers, and clusters, because symmetric multiprocessors and multi-core computers are, of course, discussed in some other chapter. Now, the symmetric multiprocessor. So, an SMP can be defined as a standalone computer system with the following characteristics. Number one, there are two or more similar processors of comparable capability. Number two, the processors share the same memory, main memory, and input-output facilities, and are interconnected by a bus or other internal connection scheme, such that memory access time is approximately the same for each processor. Number three, all processors share access to input-output devices, either through the same channels or through different channels that provide path to the same devices. Number four, all processors can perform the same functions, hence the term symmetric. No? So the system is controlled, number five, by an integrated operating system that provides interaction between processors and their programs at the job, task, file, and data element. So the points 1 to 4 should be self-explanatory, because point 5 illustrates one of the contrast with a loosely coupled multiprocessing system such as a cluster. So in the latter, the physical unit of interaction is usually a message or complete file. So in an SMP, individual data elements can constitute the level of interaction, and there can be a high degree of operations between processes. So an SMP organization has a number of potential advantages over a uniprocessor organizations, including, of course, the performance. No, if the work to be done by a computer can be organized so that some portions of the work can be done in parallel, then a system with multiple processor will yield greater performance than one with a single processor or at the same time. Another thing is the availability. So in a symmetric multiprocessor, because all processors can perform the same functions, the failure of a single processor does not halt the machine. Instead, the system can continue to functions at reduced performance. So incremental growth. Another thing is incremental growth. A user can enhance the performance of a system by adding an additional processor. Another thing is scaling. No? Vendors can offer a range of products with different price and performance characteristics based on the number of processors configured in the system. We need to remind that it is important to note that these are potential rather than guaranteed or benefits. The operating system must provide tools and functions to exploit the parallelism in the SMP system. An attractive feature of an SMP is that the existence of multiple processor is transparent to the user. So the operating system takes care of scheduling of tasks on individual processor and of synchronization among processor. In this figure, no, so the symmetric multiprocessor organizations, it illustrates the general organizations of an SMP. Now, there are multiple processors, each of which contain its own control unit, arithmetic logic unit, and register. So each processor has access to a shared main memory and the input-output devices through some form of interconnections mechanism. So a shared bus is a common facility. The processor can communicate with each other through memory. Of course, messages and the status information left in shared address spaces. It may also be possible for processor to exchange signals directly. So the memory is often organized so that multiple simultaneously accesses to separate blocks of memory are possible. So in modern computers, processors generally have at least one level of cache memory that is private to the processor. This use of cache introduces some new designs considerations because its local cache contains an image of a portion of main memory. If a word is altered in one cache, it could conceivably invalidate a word in another cache. So to prevent this, the other processor must be alerted that an update has taken place. And this problem is known as the cache coherence problem and is typically addressed in hardware rather than by the operating systems. So how about the multicore computers? A multicore computer, also known as chip multiprocessor, combines two or more processors called cores on a single piece of silicon called a die. So typically its core consists of all of the components of an independent processor such as registers, ALU, pipeline hardware, and control unit plus L1 instruction and data caches. In addition to the multiple cores, contemporary multi-core chips also include L2 cache and in some cases L3 cache. The motivation for the development of multi-core computers can be summed up, of course. Now, for decades, microprocessor systems have experienced a steady, usually exponential increase in performance. And this is partly due to hardware trends, such as increase in clock frequency and the ability to put cache memory closer to the processor because of the increasing miniaturization of microcomputer components. Performance has also been improved by the increased complexity of processor designed to exploit parallelism in instruction, execution, and memory access. So in brief, designers have come up against practical limits in the ability to achieve greater performance by means of more complex processors. Designers have found that the best way to improve performance to take advantage of advances in hardware is to put multiple processors and substantial amount of cache memory on a single chip. Of course, at present, an example of a multi-core system is the Intel Core i7, which include 4 x86 na processors. So it's with a dedicated L2 cache and with a shared L3 cache. No? That's what we have here. No, the Intel Core i7 block diagram. The Core i7 chip supports two forms of external communications to other chips. No? The DDR3 memory controller brings the memory control for the DDR or double data rate, no? Main memory onto the chip. The interface supports 3 channels that are 8 bytes wide for a total bus width of 192 bits of an aggregate data rate of up to 32 GB actually, no? With the memory controller on a chip, so the front side bus is eliminated. The quick path interconnected or the QPI is a point-to-point link electrical interconnect specification. So it enables high-speed communication among connected processor chips. The QPI links operate at 6.4 GTs or transfer per second. So at 16 bits per transfer, that adds up 12.8 GBs, and since QPI links involve dedicated bidirectional pairs, the total bandwidth is 25.6 GBs. Okay, so I think that's it for a computer system. So I think you're done already with the computer system organizations, and this topic was discussed by your professor. So this will be my references, and thank you for attending our class. So next meeting, we have a quiz. Don't forget, of course, to join in our Google Classroom for some instructions. So thank you and good day, everyone.